Hi everyone, in this video we're going to solve two questions on classical field theory. These are actually the questions that I did in my own exam last year. But before we do that, we need to review some basics on special relativity. So in special relativity, the idea is you group space and time into one set of coordinates, which is a 4-vector. So the first entry is just the speed of light times the time elapsed from the origin. And then x here with the 3-vector notation with the arrow is still the displacement from the origin in the spatial dimensions. And so this 4-vector has components x mu, where mu takes values 0, 1, 2, and 3. So last time we were only dealing with vectors with 3 components, and it was 1, 2, and 3. And because time is usually distinguished from all the other spatial components, it takes the index 0, so that you could go up to any arbitrary number of dimensions, but time would still be the 0th index. And so the way you raise and lower these indices is using the metric tensor. So x lower mu is equal to g mu nu x upper nu. And g mu nu is the metric tensor. So it's a rank 2 tensor, so it can be written as a matrix. And for example, in Euclidean space, that's space but poorly written, the matrix with entries g lower mu nu is just the identity, the 4x4 identity. So in this case, then, like last time, x lower mu is no different to x upper mu. However, in special relativity, we live in Minkowski space. And here, the matrix with entries g mu nu, so the metric tensor in matrix form, is equal to a diagonal matrix where the first entry is 1, and then the 4 other entries are all -1. And that means the 4-vector with components x lower mu is equal to ct, because we multiply ct by, we multiply ct by 1. But the 3-vector gets a minus sign. And this metric satisfies some properties, namely that it has an inverse. So g mu nu times g upper nu lambda is equal to delta lambda mu, because it's the mu lambdath component of the identity. But because g mu nu lowers the index, this is also equal to g mu lower upper lambda. So this is an important thing to remember. So this is the first thing satisfied. And the second thing is that it's symmetric. So g mu nu is always equal to g nu mu. Okay, with this in mind, now we're going to go back over the Einstein summation convention, because it's going to be a bit different this time. Before, we saw that indices were repeated when they were, or indices were summed over when they were repeated. Now, the new Einstein summation convention which is actually the same as the old one, but in a more general way, prescribes that we have an implicit sum if an index is repeated exactly twice. So, just to be clear, this means that it features in the expression exactly twice. So, for example, x lower mu, x upper mu it features exactly twice, where one is upper and one is lower. Okay. And so here we have one lower mu and one upper mu. So this does qualify for the use of Einstein summation convention. And one other thing to note, I wrote on the blackboard earlier that mu takes values 0, 1, 2, 3. Well, in general, any Greek index, so mu, alpha, beta, they take values from 0 and then all the spatial dimensions. Whereas the Latin letters, I, J, K, L, they take values starting in the spatial dimensions. So 1, 2, 3, and so forth. Okay. So now that we know more carefully when to use the Einstein summation convention, we can reformulate Maxwell's equations in covariant form. So Maxwell's equations play a very important role in physics. And it was important that special relativity was introduced for them to be consistent in the covariant reformulation, I guess. And the key player in this is really what's called the field strength tensor. So it's called the electromagnetic field strength tensor. And so the way you would say it is F mu nu is equal to del mu a nu, where del is the partial derivative with respect to x nu. So let me just write it over here, just so we remember. Del mu is, and I guess this is a good time to say it, whenever you have a lower index in the denominator, it becomes an upper index in the numerator, so like the actual expression, and the other way around. So if this was x upper mu, then this would be del lower nu, or mu. Okay. And this field strength tensor, it's defined in terms of this A. And A, mu, are the components of what's called the four potential. And the four potential groups the, this is the four potential. It groups the scalar potential, which is defined in terms of the electric field. Which also has this ddt of, this is the vector potential. And the vector potential is defined such that the magnetic field is equal to the curl of the vector field. Sorry, the vector potential. So we have the four potential, which is defined in terms of the scalar potential and the vector potential. And Maxwell's equations, when you write it like this, they take the form d mu f mu nu is equal to 4 pi over c j nu, where j mu is the four current density, usually just referred to as the four current. And so the four vector with components j mu is c times the charge density, and then the three current density. So this is just the regular one. This expresses two of Maxwell's equations, and it's the two inhomogeneous ones, which feature a source when we're not in the absence of any charge. The other two are written like this. Epsilon, mu, alpha, beta, gamma, d alpha, f, beta, gamma is equal to 0. And here, this is the rank 4 Levi-Civita symbol. But this way of writing the homogeneous Maxwell equations motivates the definition of what's called the dual field strength tensor. So let me write it right here. So the dual field strength tensor is F tilde mu nu, or sometimes written as a curly F. And it's fine like this. F tilde upper mu nu is equal to 1/2 epsilon mu nu alpha beta, the normal field strength tensor, lower alpha beta. And epsilon with 4 indices is no different really to what we saw before. So epsilon alpha beta gamma delta is equal to +1 if alpha beta gamma delta is an even permutation of, but this time it's 0, 1, 2, 3. It's equal to -1 if it's an odd permutation, and it's equal to 0 otherwise. That's really terrible. Hold on. Otherwise. Okay. And in this case, you have to be careful. You don't have the same cyclicity. When you had 3 indices, you could permute alpha, if you had like epsilon I j k. Well, this is equal to epsilon j k I, which is equal to epsilon k I j. And the reason why that's true is because to do this, to permute it, it takes two transpositions. So if you started with an even permutation of 1, 2, 3, then you would end up with an even permutation of 1, 2, 3. So this would be equal. In the case of 4 indices, this is not true anymore. If you did a cyclic permutation, so if you went delta, alpha, beta, gamma, for example, that would actually be equal to minus itself. Because to achieve that, it would be equivalent to doing 3 transpositions, which is obviously, it will take an even permutation of 0, 1, 2, 3 to an odd permutation and the other way around. So be very careful. Okay, and so you can write the homogeneous Maxwell equations in terms of the dual field strength tensor as this. You can write it as delta or del mu F tilde mu nu is equal to 0. It's tilde. Okay. There's an extra factor of half, which just obviously disappears. Okay. And why is that? Well, here you have epsilon mu alpha beta gamma F beta gamma. So this with the F would give us 2 times F mu alpha, F tilde mu alpha. Yeah. And so here I've actually relabeled alpha to mu and mu to nu, and there's an extra minus, and there's an extra 2, but since it's 0, that doesn't matter. Okay. Okay, so now we have everything we need. We have all the ingredients to attack the two questions I mentioned at the beginning of the video. And these are going to be question 3 and 4 of the 2022 CFT exam that I sat. They'll be linked in the description. So yeah, let's get going. First, we're going to warm up with question 3, and then the big, there's going to be a big build up to part C of question 4, which is what I really wanted to cover in this video. So question 3, part A, asks us to show that when you have a conserved current, that gives rise to a conserved charge. So first we need to know what a conserved current means. So in this context, when you have 4 dimensions, so one time and 3 spatial, the intuitive definition of a conserved quantity is analogous to that if we just had time. So for example, if the time derivative of some function a of t is equal to 0, that tells you that a is just a constant with respect to time. Okay. In this context, it's going to be the divergence of the 4 current. So del mu j mu. If this is equal to 0, show that this gives rise to a conserved charge, Q. And it says locally, which is a very important word. We'll see why. So if we have a conserved charge, this means that Q, the charge, which is going to be the integral over space of the charge density. So J0, if you remember, is C times rho, where rho is the charge density. You can bring out the C outside and group it with the charge if you want. It doesn't really matter. It's just a number. If Q is conserved, that tells you that d dt of Q is 0. But we need to show that. Okay, so d dt of Q is going to be equal to the integral over 3 space of d3x times the time derivative of J0. And actually here I think, see rho, C. Yeah, you could actually even divide by C here if you wanted to, because then that would give you the integral over 3 space of the derivative with respect to the 0th x component, which is just ct, of J0. Okay, so we only have one thing to go off of, so we're going to use it. This is a sum because we have an index mu which is repeated exactly twice, once lower and once upper. And it's a sum over all the possible values. So it's d0, J0 plus d1, J1 plus, or d del 2, J2 plus del 3, J3 is equal to 0. I'm going to group this and call it the divergence of the 3 current, which is, that's what it is. And so that tells us then that del 0, J0 is equal to minus the divergence of the current. Okay, so now we're going to substitute that into here. We're not. We're going to erase the board. Be civilized. We just showed that del 0, J0 is equal to minus the divergence of 3 vector. Okay, so if we plug it into here, that's going to give us minus the integral over 3 space of exactly that. So I should really be more careful. So this is J with an arrow on top. That's shorthand for J with a dot with an arrow on top. But this is the integral of a derivative. So we can take the antiderivative. So this is equal to minus J evaluated basically on the boundary of R3. But the boundary of R3 is going to be minus infinity to infinity, minus infinity to infinity, and minus infinity to infinity. And so that is the opposite of local. Local means around some place, which means you can't go up to infinity. So if the charge, or if the current is conserved locally, that tells you that outside of some region in R3, it's just 0. So I guess it's on like the boundary of R3, that's just 0. But if you look at the left-hand side, that's the time derivative of Q is equal to 0. So therefore, Q is constant. Or in other words, when you have a locally conserved current, that gives rise to a constant charge. Okay, now we're going to do part B. So in part B, we are tasked to find the energy momentum tensor and show that it is symmetric. So the first thing that you would need to know when you're going into the exam is that T mu nu is defined as the following. It's the derivative of the Lagrangian density with respect to the derivative of the field in the Lagrangian times d nu phi minus g mu nu times the Lagrangian. Okay, and we're given in this case the Lagrangian we're considering is that of a scalar field, and it's written like this. It's 1/2 g alpha beta del alpha phi del beta phi minus 1/2 m squared phi squared, the master. Okay. So here we're going to learn an important trick, and that is that when you have this kind of quadratic in something with an index, we're going to be careful, but we're going to see that there is a shorthand way of doing it. Okay. So let's just plug in the Lagrangian and see what that gives us. Okay, so this is equal to the partial derivative with respect to mu of phi of the Lagrangian, so let me just put it in, 1/2 g alpha beta del alpha phi del beta phi minus 1/2 m squared phi squared. And then I'm not even going to bother with this one. Okay, so here we see that we have a product of terms. 1/2 is constant, g alpha beta is constant. It's just, as we saw earlier, this is actually, I forgot to say, when g has upper indices, it's called the inverse metric. Because when you multiply the metric by the inverse metric, as we saw earlier, you get the identity. So that's why g upper alpha beta is the inverse metric. Okay, so these two are constant, and then we just have basically two terms that we need to take the derivative of. So we have to apply the product rule. This term is going to drop out because just like q and q dot are independent in the discrete Lagrangian formulation, in the field formulation, phi and phi dot, which is just the derivative of phi, are also independent. So this term is going to drop out in the derivative. Okay, we're going to get 1/2 g alpha beta, and I'll apply the product rule. So the product rule in the first one is going to give us the derivative of this respect to d mu phi, which is only going to be 1 if they're the same index. So there's a word for that, it's the Kronecker delta. And as I said, because mu is lower in the denominator, it becomes upper. So it's del mu alpha times d beta phi. And then here it's going to be the other way around. It's going to be d mu beta d alpha phi. And then this term hasn't changed. Okay. So let's be a bit clever here. Alpha is an index which is repeated twice, once upper and once lower, so Einstein summation convention is being used here. And it's being summed over, and that means that g is only going to be, this expression will only be non-zero for the first term when alpha and mu are the same. So it's going to give us g mu beta. So g mu beta times del beta phi. But g acts as raising and lowering. So if we have g mu beta del beta, this is just going to give us d mu upper. Oh, and I forgot expression. So this should be, thank you for pointing it out, Charlie, that I forgot del nu phi. Charlie didn't point it out, that's why I said it. So this is going to give us 1/2 g mu beta del beta phi del nu phi plus 1/2 g, here's it, it's going to be alpha mu del alpha phi del nu phi. And then minus the same thing that we haven't touched ever. Okay, but here, this is just the act of raising the index on the del, so it's going to be, we're just going to get twice the same thing, basically. So we're going to get 1/2 del mu phi, del mu phi del nu phi plus 1/2 del mu phi del nu phi, which is going to be 1 times del mu phi del nu phi. And so these are just two terms multiplying, minus g mu nu times the Lagrangian. So because they're just two terms multiplying, we can switch the order of them. So we can write that as del nu phi del mu phi. And as I told you, the metric tensor is symmetric, so we can write that as what happened to the half? So these two terms are the exact same. Yeah, they just add. Because here we're contracting beta, and so we're going to get del upper mu. And then here it's the other way around, it's alpha. It doesn't matter that alpha is on this side of the G because G is symmetric. So you could just switch these if you wanted to like look more familiar where the indices are contracted. Usually we want to write them next to each other because then when the reader sees the expression, they can spot that they're being contracted easier. If you had something like epsilon mu alpha beta gamma delta x mu, it's harder to see that mu is being contracted here because the mu is all the way to the other side of the epsilon, right? Okay, so this is, where was I? This is g nu mu times the Lagrangian because the metric tensor is symmetric. But this is, if we compare this and this is equal to t mu nu, and this is equal to t nu mu, which means that t mu nu is symmetric. So the energy momentum tensor is symmetric. And that was part B. I'm going to leave question 3 part C as revision because it is just in the notes. You have to find the associated conserved charge with t mu nu. Okay, so as I said, I'm going to let you try part C. I actually forgot as well, in part B, you have to show that it's conserved as well. So you just have to do d mu, t mu nu, and use the ordered Lagrange equations. I trust you can do that. But we're going to move on to what we really wanted to do this video, which is do question 4. So question 4 is at the very end of the exam. It has this big scary theta. That's okay, we will take care of it. And, okay, so what is question 4? That's a pen. We are given the modified Maxwell equations. So if you remember earlier, the inhomogeneous Maxwell equations were given by this expression, and the homogeneous ones were given by this. Well, we're going to modify it, and we're going to say that just like there's a 4 current, there's going to be a 4 dual current, or dual 4 current. Well, anyway, it has a tilde, and it has the same 4 pi over c in front of it. And the first thing that we have to show is that this new current is also conserved. Okay. So let's do that. It's part A. Show that's conserved. In part B of question 3, we just saw that when you have when you take the derivative of a quadratic when it has indices, it kind of looks like just taking the derivative of the quadratic normally, and you replace then the index appropriately. In that case, it meant we're replacing it with mu, because I'll let you think about why that is. But in this case, we're going to discover a new trick, or a new important recurring feature of index notation. And that's when you have, as we will see, a symmetric term is being contracted with an anti-symmetric term. So we're tasked to show that j tilde nu is conserved. I've been using mu and nu, but you could use alpha and beta, or rho and kappa. It doesn't matter, just any Greek index. Or in the exam, if you really wanted to, you could use any index you want as long as you say it at the beginning, but that would be a little bit difficult for the examiner. So let's not do that. So here we have the divergence of j tilde. So that's going to be equal to, well, we only have one equation, so let's use it. It's going to be equal to c over 4 pi del nu times the other side, which is going to be del mu f tilde mu nu. Quick sanity check. Are there any free indices. No. Here we have mu being repeated once on the bottom and once on the top. So Einstein summation convention is being used. So there's no free index on the left-hand side. And on the right on the left-hand side, and on the right-hand side, it's the same thing. So all of the indices are dummy indices. No offense. So here we have c over 4 pi times del mu f tilde mu nu. So it's the second derivative of the dual field strength tensor. And as I just mentioned at the beginning, because the partial derivatives commute, so you could do del nu first and then del mu, or the other way around, this is symmetric. Whereas, now let's see why f tilde mu nu is antisymmetric. So, a little aside here. F tilde mu nu is equal to, well, 1/2 epsilon mu nu alpha beta f alpha beta. So that's equal to minus epsilon nu mu alpha beta f alpha beta. Because if you do one transposition, you go from an even to an odd, or an odd to an even permutation of 0, 1, 2, 3. But this is just equal to minus f tilde nu mu. Okay, so now that we know that f tilde is also antisymmetric, just as f is, we know that this is a symmetric expression being summed along with an antisymmetric one. So this is antisymmetric. And it's 0. And I'm going to show you explicitly why it's 0 and why it's always going to be 0 when you have a symmetric that's being summed over with an antisymmetric. So this is equal to c over 4 pi times, I'm going to switch the order of the derivatives, and I'm going to switch the order of the indices in f. And so this will give me a plus sign, because I'm allowed to switch them because it's symmetric, but because this is antisymmetric, we're going to get an extra minus sign. So it's going to be del nu minus f tilde nu mu. Okay, so let me bring it here. Minus c over 4 pi. But now what I'm going to do is, I'm going to relabel mu as nu and nu as mu. So here I'm just relabeling indices. I'm not changing the expression, I'm just relabeling the dummy indices. So nu goes to mu and nu goes to mu. Okay, but wait a second. We have this expression here, and also here. So something equal to minus itself is 0. But this could have been any symmetric term, and this could have been any antisymmetric term. So in general, it's very important to remember when you have a symmetric expression being contracted with an antisymmetric one, you're going to get 0 for the exact reason. Because you can switch the order of both of them, get a minus sign, and then relabel the indices, ending up with the exact same expression. Okay, so we've showed that the current is conserved. Well, this is 0, therefore J tilde is conserved. In the exam, or in general, you want to make sure that you're finishing the train of logic. So we want to show it's conserved because, or we want to show it's 0 because then it will apply it's conserved. Okay, and then now let's do part B. And part B asks us to show this daunting identity, but we're going to do it in a kind of a cheeky way. So let's just recall what the, actually no, let's just do it right now. So part B asks us to show that minus 1/2 mu alpha beta gamma epsilon mu rho sigma kappa times del rho f sigma kappa is equal to, I guess, del alpha f beta gamma plus del beta f gamma alpha, so just a cyclic permutation of the 3 indices, plus d gamma f alpha beta. So it's asking us to show this, right? But what we're going to do is we're going to show that this is equal to something, which is also equal to that, which is 0. And to do that, we're going to write out f explicitly. So on the left-hand side, excuse me, on the left-hand side, we have not the whole left-hand side, just this bit here. So epsilon mu rho sigma kappa del rho. And now I'm going to write out f explicitly. It's going to be d sigma a kappa minus d kappa a sigma. What is that equal to? The epsilon doesn't change. Del rho del sigma a kappa minus epsilon mu rho sigma kappa del kappa, del rho del kappa a sigma. You're going to get very good at writing Greek indices in no time. Trust me. So here we have a symmetric expression being contracted with an antisymmetric one in exchange of rho and sigma, right here. So this is 0, right? Because we could switch these two around and then switch rho and sigma around, get an extra minus, and then relabel rho sigma and sigma rho. And then here we have to do a little bit more work because here it's not obvious that we're one transposition away. But we can bring it to that by switching sigma and kappa. So this is going to be equal to plus epsilon mu rho kappa sigma times del rho del kappa a sigma. And so here again we have something antisymmetric with respect to the exchange of indices rho and kappa, and here it's symmetric. So that would give us 0. So the left-hand side is equal to 0. What about the right-hand side? So the right-hand side, again, I'm going to write it out explicitly. So it's going to be del alpha, del beta, a gamma, bear with me, del gamma, a beta, plus del beta, del gamma, a alpha, minus del alpha, a gamma, plus del gamma, del alpha, a beta, minus del beta, a alpha. Okay. What is that equal to? Let's write it out. So we're going to have del alpha, del beta, a gamma, minus del alpha, del gamma. The alpha is kind of like a sideways gamma. A beta plus del beta or beta del gamma a alpha minus del beta alpha a gamma plus the last ones, we're almost there, del gamma del alpha a beta minus del gamma del beta a alpha. Okay, and if you can read my writing, then you'll see that there's actually a cancellation here. There's a perfect cancellation. So because the derivatives, we can switch the order of the derivatives. Here we have del alpha del beta e gamma, which is the same as here. Here we have, so these cancel. Here we have del alpha del gamma a beta, which is the same as here. And you have a minus and a plus, so they cancel. And then finally you have del beta del gamma a alpha, which is what we have here. And one has a plus, one has a minus, so these cancel. And so these are both 0. Or sorry, the 6 terms add to 0. And so we show that the right-hand side is equal to 0 and the left-hand side is equal to 0, because if you multiply minus 1/2 epsilon mu alpha beta gamma by 0, you still get 0. So this is equal to 0, and we're done. And so in question 4, part C, we're asked to use this thing that we just derived. Well, it's not necessary, but I guess I don't know how to do that. We're going to use the identity that we just derived to show that given the symmetric energy momentum tensor, which is defined as theta, It can also be defined in terms of t, but that's in your notes. Given this symmetric energy momentum tensor, show that its derivative is equal to this. And you should know, if you've been studying, that the derivative of theta is actually equal to this alone. And that's because usually j tilde is equal to 0. So this still makes sense. But to get back to the original Maxwell equations, you set j tilde to 0, and then you get your familiar relation there. Okay. So to show this, we're going to start with what we have, which is the expression for theta, and we're going to take the derivative with respect to mu or nu, because it's symmetric. You can pick. We're going to do mu. Okay. So this is what we want to show. Is equal to, where I'm going to write 4 pi times this, so that we don't have to carry it around every time, is equal to d mu times f mu upper lambda lower. And here the order does matter. So if we had lambda lower and mu upper in the other order, then we get a minus times this. So you have to be careful with this. And also if you ever typeset it, because because subscripts and superscripts don't interfere, you have to add an extra space in LaTeX or whatever you use. Okay. So f mu lambda times f lambda nu plus 1 over 4 g mu nu f lambda rho f lambda rho. Okay. So we have to apply the product rule twice on this product and on this product. So on the first product, we're just going to get mu f mu lambda times f lambda nu plus f mu lambda d mu f lambda nu plus 1/4 g mu nu times, I guess we'll start with the first one, but here actually we have something that's, again, quadratic in something, so you can do that explicitly if you're not used to it yet, or you can realize that this is the same thing as twice this term, because it's quadratic, so if you had like d dx, that's not x, d dx of x squared, that's going to be 2x. So we get an extra factor of 2, which brings us 1/4 to 1/2, and then f lambda rho d mu f lambda rho. And here it does not matter if you choose the one to be in the derivative, if you choose it to have upper or lower indices, because you can write this as the metric tensor. So I guess we'll write this here. F lambda rho is equal to, I don't know, f alpha beta, g alpha rho, g beta, or sorry, alpha lambda, g beta rho. And then these metric tensors would contract with the term in the derivative, and you would essentially switch which one is upper and which one is lower. So that doesn't matter. Okay. Okay, so now let's identify that this is just the inhomogeneous Maxwell equations, except that instead of having f upper mu lambda, we have f upper mu lower lambda, which means we have to write this as 4 pi over c times j lower lambda times f lambda nu. And so you can tell in the question that this is already the first term, because if you switch lambda and nu, you're going to get exactly the first term in the desired expression. So that's good. Now, if you were doing this in exam, your goal would then be to show that this is equal to the second term. And so to do that, we have to realize something, which is that the second term has f tilde and j tilde. And because of that, it's basically quadratic in f tilde. And so that means it has to have 2 epsilons with 4 indices, multiplying each their own f. And this is just something to notice, because whenever you have these long expressions with those indices, what you're really looking for is you're looking for a way to transform this into what you want, rather than kind of going somewhere with this blindly and then hopefully it pops out. So we want to introduce these two epsilons in some way. And because the hint tells you to use this identity, this seems like the most obvious way to do it. But in this hint, we have 3 factors, right? And here we only have 2. So now you're thinking, okay, how the hell do I do that? But you should notice that one of them has a half, and the other one has a 1 in front of it. So that's a half plus a half. So essentially, it looks like 2 terms are grouped here, and then you have your third term here. Okay, so if we put all those ingredients together, what we want is we want to have 3 terms that look like this, that are something multiplying this, such that we have all upper indices that are a cyclic permutation, and one of them has to be nu. Why is that? Because here, G mu nu can be contracted with this lower mu to give us an upper nu. And nu is a free index, but it's fixed on the left-hand side. It's fixed to be upper index on the left-hand side, and it features in the derivative here, so plus a half, sorry. So that means that one of these 3 indices that are being cyclically permuted has to be nu. Okay, so that means that the other 2, the derivative, has to have an index which is a dummy index, which is not nu. Okay, so let's write this as a sum of itself, or half itself, twice. So plus 1/2, and just so that we have it in the right form, what I'm going to do is, oh, something went wrong here, hold on. No, everything is fine. What I'm going to do is I'm going to bring the mu that's associated with the derivative, and I'm going to turn it into an upper, and to do that I have to bring the other mu, turn it into a lower. So in other words, what I'm doing is I'm writing this mu as I just showed here, G something mu, and then it's contracting with this one, making it an upper, and switching like that. Okay, so F lower mu lambda, the upper mu F lambda nu, and then the same thing again, F lower mu lambda, del mu F upper lambda nu, and then this term that I haven't touched. Or, sorry, I'm gonna change it. As I just showed earlier, you can change which one has upper indices and which one has lower indices inside the derivative. So because we want them all to have upper indices for this identity, we're going to put the upper indices inside the derivative and have the lower indices outside. So lambda rho del nu F lambda rho. Okay. And so here we are. This is almost the last step, basically. We have to identify these indices in such a way that it looks like this. So the first thing that we notice is that nu is in the second position in both of these, and we need to change that because here no index is in the same position 3 times. So let's just choose this one, and we're going to switch the order of nu and lambda. Okay, so yeah, so this is going to be equal to 4 pi over c j lambda F lambda nu. Again, this term features in the expression that we want at the end, so we're not really allowed to touch that if we want to get the right answer. Plus 1/2 F mu lambda d mu. Now I forgot which one I was going to switch. It doesn't matter actually. I'm going to switch this one. Minus F. So let me write the minus outside. Minus 1/2 F mu lambda d mu F nu lambda. Okay, but none of the terms here have a minus sign, so we can't have a minus sign given that this one has a plus and we don't really want to change it. So what we're going to do is we're going to switch the indices of this F as well to get an additional minus sign to give us a plus overall. Okay. So we're going to get plus, and here it becomes lambda mu. Okay. And it may not look like it, but we're pretty much there. lambda rho d nu f lambda rho. Okay, now what we're going to do is we're going to identify indices. So we're going to start basically labeling them differently. So here we have nu lambda rho. Because we don't want to get ourselves confused, it's always a good idea when you're relabeling, use new indices that aren't already in the expression. So we're going to use alpha and beta. So we're going to have this expression, instead of gamma, it's going to be nu. So if instead of gamma, it's going to be nu, this means that here we're going to have, so in this one, it's going to be lambda is equal to alpha, and then rho is equal to beta. And then in this one, we're going to have, let's see. So if this is nu alpha beta, then we're going to go back one cyclic permutation, and this is going to be beta. Hold on. I guess this is the one that goes back one cyclic permutation. So if we go back two cyclic permutations, or one in the other way, there should be alpha beta nu. So here mu is equal to alpha, and lambda is equal to beta. Yeah. Okay. And then the final term, the way we relabel it properly, is I don't know why it has it red there. Is so we have nu in the second position, so that corresponds to gamma in the second position. So the first one has to be beta, and the last one has to be alpha. So here mu goes to beta, and lambda goes to alpha. So basically the opposite of this. Okay, and if we put that all together, what do we get? 4 pi over c j lambda f lambda nu plus 1/2. So nu goes to beta and lambda goes to alpha. So it's going to be f beta. Hold on, I did something wrong here. No, f alpha beta times. I'm going to factorize everything, because if you notice here, this becomes f alpha beta out front. This also becomes f alpha beta, and this also becomes f alpha beta. So I'm going to factor out 1/2 f alpha beta from these three terms, and what's left in the sum is going to be del alpha f, sorry, del beta, right, because mu goes to beta, f nu alpha plus del alpha f beta nu plus del nu f alpha beta, which is exactly what we wanted. So we've somehow used all our ingredients to make the identity that we need to use. Okay. And so let's bring it back to the top of the board and then plug it in. So this is equal to 4 pi over c j lambda f lambda nu plus 1/2 f alpha beta. And now I'm going to plug in the expression. So we don't really need this anymore. I'm going to plug in this identity. So we're going to get minus 1/2, but I'm going to do it in a way which has a bit of foresight. So because, as I said, we want to have, ultimately we want to have two copies of f tilde, one which will become j tilde and the other one which will remain f tilde. We want to have a situation where we have 1/2 epsilon times two indices, which will be the indices of the f tilde, and the other two indices will be the indices of the f, which is multiplying it. So we have to have something, two indices and alpha beta. So what I'm going to do is I'm going to do two transpositions. So I'm going to fix mu, and then I'm going to bring gamma here and then here. So it's going to turn into plus gamma alpha beta. Or sorry, nu was playing the role of gamma, remember? So epsilon mu nu alpha beta. Here the sign doesn't change because I'm doing two single transpositions, which means that if it was an even permutation of 0, 1, 2, 3, it still is an even permutation, and the same for an odd permutation. And we're multiplying the same epsilon that I haven't changed down below. Del rho f sigma kappa. Okay. Now, this is where it gets exciting because we're almost there. So I can erase this. So probably you can see where this is going already, but let's do it properly. So this is 4 pi over c j lambda f lambda nu plus, now the definition of the field strength, or the dual field strength tensor, is f tilde mu nu is equal to 1/2 epsilon mu nu alpha beta f alpha beta. So this is what I was saying, basically. You want to have the two indices that are in front of the four indices to be the ones that are going to be the indices of the f tilde, and the two ones that are at the back to be the indices of the f. And this is a very poorly drawn alpha. Okay, so we have our, this is exactly, so we have 1/2 f alpha beta, let me show it up, 1/2 f alpha beta mu nu alpha beta. And then we're going to have another factor, which is going to be del rho, doesn't really matter, times, we're going to have 1/2. So notice we had 2 1/2s to start with. We still have 2 1/2s. And I forgot the minus sign, so I'm going to bring the minus sign out, put it here. 1/2, and we're left with, let's see, epsilon mu rho sigma kappa f sigma kappa. Okay, and here we just have two f tildes basically. So 4 pi over c j lambda f lambda nu minus f tilde mu nu d rho of f tilde mu lower rho. Okay, and let me think. Did I do something wrong? Yes. No, I didn't. Okay, that's fine. I was getting confused. I thought there was going to be an extra minus sign. There it is. So here, it's 4 pi over c j lambda f lambda nu minus f tilde mu nu. And these are the modified Maxwell equations now. But notice that the derivative is with respect to the second index, not the first index. So we have to switch it, which is going to give us a plus sign, and that'll become del rho f tilde rho mu. But that's just equal to 4 pi over c j lower mu. Sorry, j tilde lower mu. So here we have it basically. This is going to be equal to 4 pi over c j lambda f lambda nu plus 4 pi over c j tilde. I'm going to relabel mu as lambda here so that it looks like the final expression in the exam. F tilde lambda nu. And to get to the final expression, we divide across by 4 pi. And we switch the indices here so that when we move the j to the right, the contracted index is also to the, or is right next to the j basically. So minus f nu lambda j lambda over c minus f tilde nu lambda j tilde lambda over c. And that is it. And that's the expression we want to get to. And this basically showcases all of the important tools that you need to have when you're doing questions that involve Einstein Summation convention and raise and lower indices in this context. Okay, so let's wrap it up with some bonus questions, and then that'll be the end of it. So if you fully understood these concepts and the notation, then you should be able to answer these questions. So these are some bonus questions that I'm going to leave to you as homework. First bonus question is going to be writing the matrix whose entries are given by the mu nth component of the field strength tensor. So what is this in matrix form? It involves E's and B's and C's, and sometimes no C's depending on what units you're using, so be careful. The next bonus question is going to be, what is del mu x mu? Next we have, under what circumstances? So, in what spaces do we have epsilon upper alpha beta gamma delta equal to plus or minus epsilon lower alpha beta gamma delta? I'll give you a hint. If you just look at the metric and what values it takes and the signature, which is just how many pluses you have and how many minuses you have, you should be able to figure this out. And then also, what is epsilon alpha beta gamma delta times what is this equal to? So we saw in the last video we had a identity which was epsilon ijk equal to 6. And I guess you should ask yourself, why is it 6? How do you get to that? And so here you can lower indices because it's in Euclidean space. But here it matters, specifically in this way. So what is this equal to in Euclidean space and in Minkowski space? Yeah, so that's it. So if you have any videos about any of the questions I went through, you can email me. There'll be an email down below in the description. If you want to see more videos like this, please leave a comment and ask us what you want. Maybe next video we'll do something on differential geometry. So I guess that's the next step up, is to look at basically where you get this metric tensor and the Christoffel symbols. So some of you who are enthusiasts might have seen this before. So that appears in the covariant derivative. So yeah, if you want to see that, let us know. Thank you very much for watching. If you're confused, leave a comment. And that's it. Oh, I forgot to say, the TPSA is now sponsored by Hagoromo, which is now just Hagorome because I've written too much. But use code TPSA, is that it, for 10% off?
Code TPSA 10% off.
Use code TPSA 10% off. It'll be in the description to get some Hagoromo chalk by Full Touch. So thank you.